Hello students, in this video we have last additional exercise problem of chapter 6. Question is, line charge lambda per unit length is lost uniformly onto the rim of a wheel of mass m and radius r. The wheel has light non-conducting spokes and is free to rotate without friction about its axis as shown in figure. A uniform magnetic field extends over a circular region within the rim. It is given by B is equal to B0 K cap, and it is only for the distance up to A, and A is less than the total radius. Otherwise, magnetic field is 0. The question is, what is the angular velocity of the wheel after the field is suddenly switched off? So there is a wheel and the magnetic field extends only up to some distance. And what is that distance? That distance is small a. So we can say that this part is a. So if you choose any small distance, say r, you have magnetic field. But the moment you cross this part, the moment we cross this boundary, there is no magnetic field. So whenever you rotate this wheel on this spokes, you have EMF induced, and it is actually only within this region where you have a magnetic field. And if you stop the magnetic field, there will be some torque experienced, and then you will have some angular velocity. So let us start with what we know, and what we know is how much is the induced EMF. So induced EMF can be given as minus d phi by dt minus d phi by dt. Now we know that phi is b into a, actually cos theta, but in this case cos theta is 1. So area, which area we should consider? Now here, though the total area, see radius of this ring is r, so should I consider a to be pi r square, or I should take a to be sorry, pi into a square? So this is not the area, this is the area. Why? Because magnetic field is only up to a, so effective area is pi a square. And so we'll consider a to be pi a square here, pi a square dB by dt. Now considering only magnitude of EMF, this can be written as plus pi a square dB by dt. Now from previous chapters, you must be knowing that potential difference can be given as over closed loop, it is E dot dl. So E dot dl is pi a square dB by dt. And if you integrate the circle, you'll get E into 2 pi r pi a square dB by dt. So on simplifying, we get a square upon 2r dB by dt. Now we know that force in electrostatics can be given as F is equal to QE. Hence, here I should be able to write this as F by Q as a square upon 2r dB by dt. And then F becomes a square Q by 2r dB by dt. Now there will be a force according to this equation, and in this rotational motion there will be torque also. So the torque acting can be given as, we know that tau is r cross f, but in this case Instead of RF sine theta, we will write RF only because sine theta will be 1. You can verify from the figure direction, and we know that tau is also I alpha. So it is I alpha, which is equal to RF. Now don't forget here that I is moment of inertia. It is not the current. Okay. So moment of inertia is mr square. Alpha is d omega by dt, angular acceleration. Radius of the disk ring is capital R, and force, as from previous equation, we have a square q by 2r into dB by dt. Again, what is m here? M is mass of the ring. So simplifying this, we get m d omega by dt is equal to a square q by r square dB by dt. In fact, we know that lambda is line charge density and it is charge per unit length. Length here is the circumference, so it is q by 2 pi r. So substituting this and simplifying, we get m d omega to be equal to a square lambda 2 pi r dB over r square. My mistake, it is not small r, it is capital R. So 2 pi r dB. And on further simplification, we get d omega to be a square lambda into 2 pi dB by mr. I think I made one mistake. I forgot this 2 here. So we will have 2 and 2, and then the expression will be d omega is equal to lambda a square pi dB over mr. Now if you want omega, you should integrate both sides. So d omega is equal to lambda constant a square pi, both are constant, upon mr integration dB. And then we will end up with the expression omega is equal to lambda a square pi. Integration dB will give you b, and value of b is b0 here upon mr. So this is the angular velocity which we will observe when magnetic field is switched off. And that was the problem. Thank you.